Welcome back. It is so good to have you here with us again. Grab a seat, get comfortable.
Yeah, definitely. It's great to be back.
We spend so much of our time just sort of skimming the surface of the information that constantly floods our feeds.
Oh, constantly. It's overwhelming.
Right. But today, we are doing what we do best. We are pausing, we are zooming out, and we are diving deep. I'm talking about looking at the very architecture of reality alongside a true friend of the curious mind.
I like the sound of that.
Today, we're exploring a deeply fascinating conversation from this show, featuring David Krakauer, who is the president of the Santa Fe Institute.
And it really is a remarkable conversation to dissect. Krakauer brings this incredibly unique perspective that somehow manages to span evolutionary theory, computer science, physics, and mathematics.
All at once.
All at once, yeah. And all without losing sight of what it actually means to be human.
Exactly. And our mission for this deep dive is to explore some of the most profound questions of our very existence. We're going to figure out what complexity actually means in a scientific sense.
Right, the real definition.
We'll explore the startling and frankly game-changing difference between AI capability and true intelligence.
That's a big one.
It is. And if that wasn't enough, we're going to look at the ultimate purpose of life in the universe.
Just light, easy topics today.
Just the light stuff. I promise you, by the time we wrap up today, you are going to completely rethink your relationship with your smartphone, the AI tools you use at work, and maybe even the spontaneous thoughts popping into your own head. Okay, let's unpack this.
It all really begins with the unique mission of the Santa Fe Institute itself. Their goal is elegantly simple to state, yet incredibly daunting to actually execute, which is searching for order in the complexity of evolving worlds.
Which sounds huge.
It is. It's an entire institution dedicated to finding the hidden patterns and the absolute chaos of life.
And the origin story of the Santa Fe Institute, or SFI, is fascinating all on its own.
Oh, absolutely.
Picture the setting. It's deliberately placed in the high desert mountains of New Mexico, out in the middle of nowhere, very close to the Los Alamos National Laboratory.
Right, the Manhattan Project facility.
Exactly. That's the facility famously associated with nuclear research.
Yeah.
You put a place like that in the middle of nowhere for a reason, and SFI sort of shares that overlapping genetic history of bringing brilliant, isolated minds together.
It does. And the intellectual spark for SFI actually traces back to the 1950s.
Let's hear it.
Well, the founding president, George Cowan, was a child prodigy who had worked alongside Nobel laureates like Eugene Wigner and Enrico Fermi.
Heavy hitters.
Serious heavy hitters. So in the early 50s, Cowan is invited to give a talk at the Aspen Institute in Colorado. He stands up in front of this room of academics and decides to speak on a concept he calls social entropy.
Which sounds like an incredible concept. But wait, entropy is a law of physics, right?
Right.
It's the idea that closed systems naturally tend toward disorder and chaos over time. How does that mathematical law apply to human society?
That is exactly what Cowan was trying to figure out. He was essentially arguing that human societies are not exempt from the laws of physics.
Oh, interesting.
Yeah. Without constant energy input, meaning cultural norms, laws, institutions, and effort, societies will naturally decay into disorder.
So it takes work to maintain order.
Exactly. He was asking, what if this mathematical law of physics can be mapped directly onto human civilization?
That is profound. So how did the room react to that?
The talk completely bombed.
Oh, no.
Oh, yeah. Nobody in the room understood what he was talking about.
Seriously.
Yeah. The physicists didn't get the social application, and the sociologists didn't understand the math. They couldn't tell if he was speaking in metaphors or presenting actual rigorous equations.
Ouch. A spectacular failure of communication. But I suppose a highly productive one, right? Because over the next 30 years, that massive miscommunication sparked a realization among top thinkers that something was fundamentally broken in academia.
Yes.
The social sciences and the hard mathematical sciences were completely isolated from each other. They were speaking different languages.
Right, the silo effect.
Exactly. So by 1984, a group of Nobel laureates and brilliant minds decided to short-circuit that traditional academic department structure.
Yeah.
They created SFI to compress all these different disciplines into one high-density space.
Precisely. To study what they call organized complexity. Now, to really grasp where you and I fit into all of this, Krakauer points back to a brilliant framework from 1948 by a mathematician named Warren Weaver.
Oh, the three tiers.
Right. Weavers essentially divided the entire universe into three distinct tiers of scientific problems.
Walk us through those tiers, because this really frames the whole discussion.
The first tier Weaver identified is simple phenomena. This is classical physics. It doesn't mean the math is easy for you and me to do at our kitchen table, but it means the phenomena follow beautiful, elegant, highly predictable mathematical laws.
Like what?
Think of a frictionless pulley on an inclined plane, or the perfect sweeping elliptical orbits of the planets. 2 or 3 variables, easily calculated.
Right, the clean stuff. But the universe isn't usually that clean.
Exactly. So the second tier is disorganized complexity. This is where you get into things like gases and thermodynamics.
It's a lot of moving parts.
Billions of them. Imagine a massive container filled with billions of gas particles. If you try to track one single gas particle, its movement is totally irregular, erratic, and chaotic. You can't predict it.
Right.
But if you zoom out and look at the whole container, their average behavior becomes completely predictable. You can calculate the exact temperature and pressure using statistical mechanics.
Okay, so we have perfect simplicity on one end and completely disorganized statistical chaos on the other. Where do humans fit in?
That brings us to the third tier, the space where human beings actually live. Organized complexity.
The messy middle.
The messy middle. It's between perfect order and complete chaos. It's not a predictable, frictionless pulley, and it's not a random cloud of gas.
So what is it?
It's an organism adapting to a changing environment. It's an ant colony building a bridge. It's a human brain navigating a conversation. It's a bustling city.
Krakauer uses this amazing term for it, problem-solving matter. In classical physics, a ball rolling down a hill isn't thinking. It's not trying to survive. But complexity science studies matter that is actively trying to solve the problem of staying alive.
What's fascinating here is the concept of emergence. Emergence is the absolute key to understanding this messy middle. To explain it, Krakauer uses a brilliant analogy regarding fluid dynamics.
Oh, the river analogy.
Yes. When a physicist studies a flowing river, they use the mathematics of fluid dynamics. They do not need to calculate the trajectory of every single microscopic H2O molecule.
That would be impossible anyway.
Right, because when millions of water molecules come together at a certain temperature and pressure, they create a brand new state, a fluid. And that fluid has its own unique macroscopic rules.
It changes the game entirely.
Exactly. The new state screens off the microscopic details. Those individual molecular movements no longer matter at the level of the rushing river.
I love how that applies to human behavior. Let's think about the world of advertising and marketing for a second.
Okay.
A truly great marketer doesn't need to be a neuroscientist. They don't need to know how the individual sodium and potassium channels are firing in your specific neurons when you look at a billboard on the highway.
Right, they don't care about the molecules.
Because when you put millions of humans together in a market, new collective behaviors emerge. The marketer is basically practicing the fluid dynamics of human psychology.
That is a perfect way to put it. The individual microscopic details, your specific neurobiology, are screened off. The emergent level of the crowd has its own perfectly adequate language and predictable rules.
Which is humbling, but also wild when you think about it.
Yeah.
As an individual listener tuning into this deep dive, you are incredibly complex. You have your own history, desires, fears, and totally unpredictable quirks.
Very unpredictable.
But put you in a massive city with millions of other people, and suddenly you become part of a mathematical formula. Krakauer points out a mind-blowing example of this. As a city's population grows, its gross domestic product, its GDP, reliably scales to the 1.155 power.
It's crazy how consistent that is.
It scales almost exactly like a law of physics, regardless of what city it is. Our constraints force us into emergent, predictable patterns.
Yes. Individual chaos morphs into predictable structure at scale, which naturally leads to a massive question.
Which is?
If human behavior at scale is just a predictable mathematical pattern, it makes you wonder, can we just build a machine to calculate it? Which brings us to the elephant in the room, artificial intelligence.
Here's where it gets really interesting. Because if there is one topic dominating our feeds right now, it's AI. And Krakauer takes a highly provocative stance here. He argues that current artificial intelligence, the large language models everyone is using, has absolutely massive capability, but zero actual intelligence.
It is a critical distinction that we desperately need to make. We constantly confuse the ability to produce a correct result with the cognitive process of intelligence. They are not the same thing.
Okay, I have to play devil's advocate here. Wait, zero intelligence. That feels a bit harsh.
I know, it sounds extreme.
If my AI assistant can write a perfect Python script or draft an entire highly researched business proposal in 3 seconds, doing something that would take me all day, how is that not intelligent?
It's capable,
Yeah.
undeniably, but Krakauer uses a fantastic analogy here to explain why it lacks intelligence. Imagine two students, student A and student B.
Yep.
You give them both the exact same highly difficult mathematics exam, they both hand it back, and they both scored 100%.
Perfect scores.
Right. If you just look at the output, the test scores, you'd say they are equally intelligent, but then you find out how they took the test.
Ah.
Student A sat in a massive library and just rapidly looked up every single answer in an encyclopedia. Student B sat alone by the ocean with a blank piece of paper and a pencil and painstakingly worked out the underlying logic of every single problem.
Oh, wow, okay.
Right. Student A is current AI. It's a remarkably fast, highly capable lookup tool that has ingested the entire internet. It interpolates data.
This is just fetching answers.
Exactly. Student B is utilizing true intelligence. True intelligence isn't just arriving at the right answer, it's the process of taking a hard problem and making it easy through understanding.
That makes so much sense. It reminds me of the second analogy he uses, the one about the architect.
Oh, that's a great one.
Imagine you're an architect interviewing two interns and you want to test their problem-solving skills. You point out the window at a church steeple across the street and ask, how tall is that steeple?
A classic test.
The first intern immediately says, it's 135 feet. You ask how they know, and they say, oh, I memorized a list of all the local church steeple heights before the interview.
Student A.
Exactly. The second intern says, I have no idea. Give me 10 minutes. They go outside, they measure the length of their own shadow, they measure the steeple's shadow, and using basic geometry, they calculate that it's about 135 feet. Who do you hire?
You hire the second intern every single time. Because they didn't just access a massive database, they applied a logical framework to extract an answer from the physical world.
They actually solved it.
Right. If you ask the first intern the height of a steeple that wasn't on their list, they fail. The second intern can measure anything in the world.
And this really cuts to the core of why Krakauer thinks the famous Turing test was actually a disaster for computer science.
It really was. Alan Turing's imitation game essentially proposes that if a human conversing with a machine cannot tell it apart from another human, the machine must be considered intelligent.
Which sounds reasonable at first.
It does, but Krakauer argues this test did a lot of harm to our understanding of the mind because it implicitly allows for cheating. It only measures the final output.
So it's rewarding the lookup intern.
Precisely. The Turing test says, if the intern says 135 feet, they are an architect. But to truly find intelligence, you cannot just accept the answer. You must demand an explanation of how the answer was reached.
Which is such a massive paradigm shift for us right now. We're so easily fooled by a confident output from a chatbot. But if we pull back, if human intelligence is this logical process, this measuring of shadows, does that mean computation is universal? What does SFI's Interplanetary Project have to say about this?
This is where we look at life outside our human biases. Astrobiology is heavily dominated by chemistry.
Right, looking for water.
Yeah, we look for water, we look for carbon, we look for DNA, but if life is fundamentally problem-solving matter, does the specific material really matter? Krakauer uses an extraterrestrial thought experiment to illustrate this.
Let's hear it.
Imagine an alien species visits Earth centuries ago during the era of the Jacquard loom.
That's the weaving machine, right?
Yes, an early mechanical computer made of wood and silk, operated with a foot pedal, used to weave complex patterns. The aliens look at it and write down on their logs, ah, on Earth, computers are made of wood and silk. Then they leave.
Okay.
They come back 100 years later. Now we have early electronic computers using massive glass vacuum tubes and tungsten. The aliens are confused. Wait, computers aren't wood. They are made of glass and metal. They leave and come back today. Now computers are microscopic silicon transistors.
The realization those aliens would eventually have to reach is that computation has absolutely nothing to do with the material itself.
Right.
Wood, glass, silicon, those are just the physical substrates. What makes it a computer is the logic being implemented through the material.
Exactly. The material is irrelevant to the math.
So the massive question this raises for us is, could life just be a logical, computational problem-solving process? One that isn't inherently restricted to the wet biology of carbon and water? We get so obsessed with the material we are made of because it's the only example we know.
But if the material doesn't matter and computation is just universal logic, what exactly is the wet biological computer inside our own heads actually doing? What is that voice in our heads?
This brings us to consciousness.
Well, according to Krakauer, a lot of the pop science books currently flooding the shelves about consciousness are just baloney. We act like we fully understand it, but we really don't.
We don't.
Well,
The most rigorous scientific approach right now is what's called the neural correlates approach. This involves measuring brain activity mathematically.
how does that work?
You track the physical states of the brain when a person is deeply asleep versus when they are under heavy anesthesia versus when they are awake and actively solving a problem. You look for the correlations between brain states and subjective experience.
Okay, so what did that approach actually prove? Because I remember reading about a massive aha moment regarding this. We tend to think that our conscious mind, that active narrating voice in our head that we identify as us, is the thing doing the heavy lifting when we solve problems. We think consciousness is the ultimate calculator. But it isn't, is it? No, it really isn't. Krakauer cites a famous book by Jacques Hadamard called The Mathematician's Mind. Hadamard studied absolute geniuses, people like Albert Einstein, Henri Poincaré, and Carl Friedrich Gauss.
The greats.
The absolute best. He wanted to know how they solved the hardest mathematical proofs in the world, and they all reported the exact same bizarre phenomenon.
Which was?
When faced with an incredibly difficult problem, they couldn't solve it by forcing their conscious mind to stare at the chalkboard. The solution always arrived when they stopped consciously thinking about it.
They just let it go?
They'd go for a walk by the ocean or step onto a bus or play the violin, and suddenly, boom, the entire fully formed mathematical epiphany would strike them out of nowhere.
That is incredible. The conscious brain was quiet and the unconscious was doing the actual heavy computation.
If we connect this to the bigger picture, it suggests that consciousness is not this grand, all-encompassing processor we think it is.
Yeah.
It is actually just a tiny, highly restricted attention window.
To explain why our brains are structured this way, the conversation turns to a brilliant pop culture analogy from the movie I, Robot.
Such a great comparison.
In the film, there are these giant storage vans filled with decommissioned, older model robots. They are essentially deactivated, but for some reason, they're all huddling and clustering together in the dark. The characters ask why they are doing this, and the answer is that they are being driven by leftover, uncleared legacy software. Old programming that was never deleted, still running silently in the background.
That is precisely what human evolution is.
Huh?
For hundreds of millions of years, biological organisms evolved incredibly complex automatic programs to ensure survival. Programs for finding food, regulating heartbeats, recognizing faces, avoiding predators.
And we still have them.
We do. Those programs are still running in us right now. They are ancient legacy code.
It's your gecko brain, your deep instincts. And sitting on top of millions of years of automated unconscious survival software is this incredibly thin layer of conscious abstraction and self-awareness. It's doing very little of the actual computation of keeping you alive. But that thin layer has one massive superpower.
Language.
Language. It allows us to communicate our understanding to each other. I can consciously pass a complex idea from my brain directly into yours using words.
But because that conscious attention window is so small, because it can only hold a few things at once, human intelligence has always relied on outsourcing our cognitive load to tools. We use physical artifacts to help us think.
And this is where I really want you, the listener, to evaluate your workspace and your daily habits right now. Because Krakauer divides the tools we use into two very distinct categories, and the difference is vital. First, you have complementary cognitive artifacts. These are things like an abacus, a pencil and paper, or a ship's sextant. When you use these tools, you have to actively engage your understanding. They complement your thinking. The use of these tools actually makes you smarter over time. You learn the math, you learn the stars.
Conversely, you have competitive cognitive artifacts.
Yes. Things like your car's GPS or the large language models and AI chatbots you might be using at work to write emails or code. When you use these, you aren't engaging your understanding at all. You are entirely outsourcing your capability to the machine.
You're just taking the output.
Think about it. When was the last time you actually memorized a phone number? By outsourcing our memory to our phones, we've lost that mental muscle. Now apply that to navigating a city. You aren't learning the layout of the streets, you're just blindly following a blue line on a screen.
And Krakauer warns that relying heavily on competitive artifacts actually makes us dumber. We are sacrificing our own problem-solving intelligence, our ability to measure the steeple for the sake of immediate capability.
It's a terrifying thought. If we let ChatGPT structure all our arguments for us, do we lose the cognitive ability to form a logical argument ourselves?
It is a profound choice humanity is currently facing. What kind of tools do we want to be dependent upon as we evolve?
So what does this all mean? We've journeyed from the complex mathematics of cities all the way down to the legacy code running in our own brains. But Krakauer leaves us with one final, ultimate question. If life is problem-solving matter, why did the universe create life in the first place? What is the grand problem the universe is trying to solve?
He provides two answers, and they could not be more different. He starts with the horribly cynical one, which is rooted purely in physics. Thermodynamics. We discussed entropy earlier, the universe's drive toward disorder and chaos.
Right.
Well, the cynical view is that life is simply the most efficient mechanism the universe has ever generated for turning order into disorder. By building massive factories, burning fossil fuels, consuming energy, and destroying resources, life rapidly accelerates the universe's rush toward thermodynamic equilibrium.
That is dark.
In this view, life is essentially a kind of suicide by the universe.
Wow. A completely bleak but mathematically logical answer. We are just entropy engines. But he immediately counters that with a perspective drawn from idealist philosophy, the poetic answer. And the poetic answer is that life is simply the universe's way of knowing itself. The cosmos generated conscious, problem-solving matter, so that finally, after billions of years of silent physics, the universe could look in a mirror and comprehend its own existence.
It is a striking dichotomy to leave us with. We are either engines of thermodynamic decay, or we are the sensory organs of the cosmos. Perhaps somewhere in the messy middle of organized complexity, we are a bit of both.
What an incredible journey through this material. To summarize what we've unpacked today, you and I, we are problem-solving matter, navigating that messy middle of complexity. We've learned that true intelligence is about deeply understanding the how and the why, not just looking up the answers like an AI search engine. And perhaps most immediately applicable to our daily lives, we must fiercely protect our minds. We need to be highly skeptical of competitive tools that outsource our intellect, and instead seek out the complementary tools that expand it.
This raises an important question, one that builds directly on that concept of our evolutionary legacy software. If our conscious mind is mostly just a thin, narrating layer of language sitting on top of millions of years of highly automated, unconscious programming,
Yo, this is a deep one to end on.
how much of your daily decision-making is actually you making a conscious choice? And how much of it is just ancient evolutionary legacy code running silently in the background of your mind, guiding your actions and reactions before your conscious self even realizes what's happening?
A massive thought to mull over as you go about the rest of your day. Thank you so much for joining us on this deep dive into the source material. Remember to keep zooming out, keep looking for the patterns in the noise, and most importantly, keep questioning the complex world around you. We'll catch you on the next deep dive.